Finally, we want to get a brief overview of why electron configuration and quantum mechanics is important to us from a periodic table standpoint. We're going to continue to develop those ideas over the rest of this course, over the chapters that are remaining for us to discuss. We left off last time talking about the periodic table and the fact that each element in a particular column has the same type of ending in its electron configuration. Boron ends in 2p1, aluminum ends in 3p1, gallium ends in 4p1, and so on and so on. They all end in p1 in this column. They all end in p2 in this column. They all end in d5 in this column. And so those are key ingredients to us being able to understand why elements that have similar properties to one another do that. This is something that Dmitri Mendeleev noticed in the 1800s, long before quantum mechanics. When he made the periodic table, he took and placed similar elements, similar behaving elements to one another in the same column, and then kept the periodic table in order, he thought, by atomic mass. Turns out atomic number is a better way to think of it. But look at how this worked out. Copper, silver, gold in this D9 column. They actually end, a little bit of an exception to our rules, in D10 because the 4s is left half filled instead of the D. But these S1 D10 endings, they are what we call coinage metals or jewelry metals. They're very, very inert, so they make pretty good coins and pretty good jewelry. Whereas all of these S1 metals are explosive when dropped in water. And nickel, palladium, and platinum have very specific catalytic properties that are similar to one another. And we can see that throughout the periodic table. Elements that are in the same column have similar properties to one another. And it's because the outside of the atom has a similar shape to it from an electronic orbital perspective, from the way that the electrons are filled. And so those outer electrons in a particular atom we call valence electrons, they are the ones that are going to be most important in determining the properties of a particular atom. And the elements in a given group or column on the periodic table have very similar valence shell configurations. What's different is the energy level, but the sublevel and the number of electrons in those sublevels remains the same. And so again, here's a review. All of the elements in this area have configuration that end in S. We have our S1 column, our S2 column. These all end in D. Now something to notice, and this is how you can write your electron configurations. 1s2, 2s2. Let's say we wanted to write the electron configuration for iron, which is right here in the middle of what we call the 3D row. We want to write out where all the electrons are. We'd begin here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then here's where we'd have to think or remember a little bit. When we're going through row 4, the D set are one level lower than the S set. So after we said 4s2, we'll say 3D, and we'll count over to where iron is in the row, and it's the sixth element in the 3D portion of the table. So it ends in 3d6. And we can do that for any element on the table as long as we bear in mind the couple of exceptions that there are to our rules. And also remember that the 4F and the 5F block belong here in row 6. The only reason we don't place them that way is it would make the periodic table very long to fit on an 8x10 sheet of paper. So we'd go 6S and then 4F and then 5D if we were following that order. And that's a way to write electron configurations. We'll go over another way that might be easier for some of you in class next time. Now look what happens. If we look at the size of the atoms, they get larger in size as we go down the periodic table. That makes sense. Each time we add a level of electrons, the atoms get bigger. Here's what doesn't make sense, at least at first until we think about it. As we go across the periodic table to the right, the width, the radius of the atoms is getting smaller. And so someone might say, when we go from potassium to calcium to scandium and so on, we're adding more electrons. Why is the atom getting smaller? Well, we're adding more electrons and we're adding more protons. And so the protons pull in on the electrons. And so you could say, well, it should be a tie then. But what happens is, right here we're in level 4. So right here you have the number of protons that potassium has, 19. 19 protons pulling in on 4 energy levels. Here you have 20 protons pulling in on 4 energy levels. So they can pull in a little bit further. Here you have 21 protons pulling in on 4 energy levels, and so on. And so as we go across the table, we have more and more protons pulling in on the same number of energy levels, and it gets tighter and tighter and tighter until we have to add another energy level, and then we get a bigger atom. And so that's why the biggest atoms are in the lower left corner of the periodic table, and the smallest are in the upper right. And as far as size goes, we can think of hydrogen really kind of being in either spot, but over here even more so than over here. Hydrogen and helium are kind of tricky to place on the periodic table based on their trends and based on their electron configurations. Now, way back in chapters 1 and 2, we learned that what we characterize as capital Z is the atomic number. And so what we've got here is a plot of Z versus atomic radius, and that's what the red curve is, and a plot of Z versus Z effective. This gets back to this idea I mentioned earlier of shielding. Sodium has 11 protons, but the outer electron can only feel about 2.5 protons worth of pull because all of the other electrons, the other 10 electrons, are in the way. As Z goes up, Z effective goes up, almost 1 proton per level, because or per electron added and proton added, because we're not introducing any more shields. We can think of each energy level as a shield, and we stay on energy level 3 throughout the sodium row. When we get to the end of the sodium row and we go to the next row to number 19, what we're going to see is a drop in Z effective for the outer electron because another shield, another energy level, will have been completed and placed in the way. And that has its effect on atomic radius. The more protons the outer electron can feel as it reaches through the inner electrons, the tighter and smaller that atom is going to get in its width. All right, you can look these up on D2L as well, but here's the list of suggested problems from the end of Chapter 5, and we'll give a shot to working on these problems in class as we go over these concepts even more.